Hello everyone, welcome to this new lecture series on reinforcement learning. This is the first lecture of the series. My name is Dhiraj Madan and today we are starting this new course on RL. For the first lecture today we'll be introducing the topic of reinforcement learning and we'll be starting with the Markov decision process framework. Okay. What are the prerequisites of the course? What is it that you should know in advance? So, I'm assuming some familiarity with machine learning and deep learning. And secondly, you should be comfortable with maths, right? So basically, linear algebra and probability. So just some basic undergrad level linear algebra and probability, along with some basic knowledge of machine learning and deep learning will be useful. And what are the contents of this course? So basically, this is just for today's lecture. I'll be talking about it again in some time. So for this entire course, okay, so if we have to discuss the content, so we'll be starting with a basic value and okay, we'll be starting with MDP framework, which will be topic for today's class. And subsequently, in the next few lectures, we'll take up value and policy iterations. Right. And then we'll move on to RL algorithms. So starting with TD learning, Q learning, right? Uh, so we'll discuss exploration, exploitation trade-off. Yes, including bandits. So let's see if we discuss any of the bandit algorithms like UC bandits or something. And so after that, we'll move on to deep RL. So we'll discuss deep Q learning and variants of that as well. Right, and then we look at policy gradients. So we can actually take a policy gradients earlier as well. But yeah, anyways, we need to cover it. So maybe I might take it up before Q learning also because that doesn't require too much background. And yeah, and of course, actor critic. So trust region policy optimization, proximal policy optimization, right? And more recent ones like including DPO, which is specific for the RLHF framework, right? Which is more common in the LLM era. Okay. So yeah, so basically these are like the primarily the set of topics at a high level, but I may choose to include more topics or maybe delete some of these based on how the time how much time I get and how is the feedback for the course. So today we'll be discussing with the introduction. We'll introduce the topic of reinforcement learning, as well as I'll also introduce the Markov decision process framework. Okay, so let's get started. So the idea is as follows. So if you are familiar with the machine learning or more specifically in supervised learning, so there are many problems wherein you do not have a sort of a ground truth associated with the training. So it's about the supervised learning involved. So supervised learning involves training on a training set. So basically you need to train on training data, which is which consists of all these inputs and their corresponding labels. So, for example, if you let's say solving some sort of a regression problem, then you can have, let's say, a lot of these input features. Let's say you are trying to predict the uh, price of a house, then essentially your features could be the area, the locality, etc. The labels could be the corresponding price. So in other domains also you can look at several examples of the supervised learning problems. I'm assuming that you are well versed with all of that. So you can have several sort of these regression algorithms, classification algorithms, etc. But in case of reinforcement learning, why when is it that it becomes important? So there are many such problems, wherein you cannot sort of give a ground truth input. So for example, if you're training, let's say a robot, right? And if you're training a robot to, let's say navigate, a bunch of obstacles, right? So you may not have, the precise information as to, how should it balance, which foot should it put to the front, what is the angle made by the legs. There are lots of nuances to it. And often it becomes more easier to give a feedback in terms of whether the action was the correct one or not in the end, and that feedback can come naturally, right? Whether it is able to navigate those obstacles, whether it is able to reach the goal or the destination, or whether it falls behind. So all those can become some sort of feedbacks or rewards. But those are sort of easy to obtain, whereas a ground truth label, the correct action to take is difficult. And similarly, even from your own very basic daily experiences also you might see, right? So how does a child learn to ride a bicycle, right? So you might, when you would have learned to ride a bicycle, you might have just tried sort of different ways to balance your bicycle by changing the direction of the handle, by paddling at some particular speed, or controlling your sort of when to apply brakes, when to apply when to speed up your paddling. So all those things, or when to turn the handle of the bicycle. So there are lots of nuances to it. You can get some sort of basic instructions, but then after that you need to figure out yourself, right? And how do you figure out yourself? Well, you try out something, you fall down, or maybe you successfully sort of are able to ride the bike. So there are lots of all these sort of things, and it's essentially learning by trial and error, right? So if I have to define reinforcement learning, so essentially one can think of it as learning by trial and error, and often there is a notion of a feedback or reward. However, there is no ground truth label. We learn from feedback or reward, but without an explicit ground truth label. Okay, so you do not know the correct way to handle it, but then you know that, okay, once you have seen some examples wherein someone took a particular action and they failed, or someone took a particular action and they succeeded, right? And often this feedback or these rewards are also sparse in nature, so that is another sort of problem, right? So I can give you some examples, but this is at a high level. So example, uh, a robot navigating obstacles, or a human, or a child learning to ride bicycle. Okay, so these could be some examples. uh, right, so essentially you can, okay, just try to think about it. What is the sort of feedback you receive, what are the sort of actions? And actually we are just going to define reinforcement learning. So there, okay, again you will have to take that correlation. So let's continue now. Right. So essentially, reinforcement learning framework formalizes this notion of learning from feedback or reward, and many other sort of these games which you might have learned, right? So for example, chess, checkers. So all these can be cast in terms of this RL framework. So more recently, right, when these LLMs have become so common and they are quite powerful as well. So a part of the training involves, especially when you have to train these language models to be able to reason, quote unquote reason, because for now we don't even know what sort of reasoning is going on. But at whatever reasoning they are able to do, okay, so that training, it often involves this reinforcement learning stage, right? And more specifically, there is a way you can provide a human feedback for the particular response, which is called as RLHF, or reinforcement learning from human feedback. And then you can also give these rewards instead of human feedback. You can also automate this reward generation process. So, for example, if you have a code and you want to check whether that code is working well, okay, so if your model has produced a code, then you can keep some test cases, and those test cases can also generate reward. So there are all those variants which can happen, and different ways to formulate this reward or feedback. But the essential ideas, they remain the same, right? So and those are the ones which we are going to initially, at least for the initial part of the course, we are going to focus on those fundamental ideas. Okay. So essentially, this formalism of reinforcement learning is based on the idea of Markov decision processes, which we are now going to discuss. These are also known as MDPs, right? Markov decision process. So to explain this idea of Markov decision process, we are going to take a very classical example of something known as grid world. Okay. Actually, all the RL textbooks, they use this particular example, and actually it's quite simple and it explains the concepts quite well. So that's why I'm going to borrow that. Mm. So this particular example I have taken is from the textbook called AI, A Modern Approach by Russell and Norvig. Right? But the similar example is also there in lots of other textbooks as well. So consider a game, okay, which is played on a 4x3 grid. So we are taking a 4x3 grid. Okay, so basically there are 12 cells, and you start from one of these cells. Okay. And at every step, you can move either up, down, left, or right. Okay. And one of the cells is not accessible. So I'm just marking the cell. This is somewhere you cannot reach. So there is this cell is not available. But you have started from this cell. And essentially, there are these two sort of cells which are terminal cells. They have a sort of a reward associated with them of +1 and -1. At every time step, you have four possible actions. You can either go up, left, right, or down. Okay. So now we are going to, get some flavor of this Markov decision process. So now I'm trying to use the same terminology. So action here refers to, the sort of possible choices you have. And essentially, you can think of it, when you are playing a game, a computer game, for example. So whatever controls you have, which are available to you, those are, you can think of it as actions, right? So we'll again define these things formally. But right now, I'm telling you that in this particular game, there are four possible. At every cell, you have four possible choices. You can either go left, right, up, or down. Okay. And whatever are okay, and there are all these possible 11 cells available to you. This particular cell is unavailable, right? So there are okay, so this is there is something known as state, right? So state represents where are you in the particular sort of system, right? So for example, in this grid, as a player, where are you currently? What is your position? So that is indicated by state. So essentially, there are 11 possible states here, which correspond to the cells where you can be at a given point of time. And you have four possible actions at every cell, which you can try to go up, left, down, or right. And based on the action you pick, you might reach another cell. Okay, so you might think that, okay, if I've chosen the cell up, then maybe I should move up. Well, but let's make this game slightly more tricky. So how do these action function? So basically, each action leads to a transition. So every action leads to a transition. So how do these transitions, how do they work? So essentially the idea in this particular game is that you move in the direction you desire with probability. Let's say on taking action A, which belongs to, up, down, left, or right. So you move to, you move in the desired direction with probability 0.8. Okay, so let's say if I want to go up, if I choose the action up, then essentially I'll be going in the up direction with probability 0.8. However, with probability 0.1 each, you will be going in one of the two directions orthogonal to the desired, right? So let's say if I want to go up, then essentially with probability 0.1, I might go to the left, and with probability 0.1, I might go to right, and with probability 0.8, I'll go. Okay. So with probability 0.1, you have to go in 0.1 each for two orthogonal directions. So basically, let's take an example. So example, if the action goes to up, then essentially you will move up with probability 0.8, left with probability 0.1, and similarly right with probability 0.1. Similarly, if you want to go to the left, then again you will move to left with probability 0.8, but then there are two directions orthogonal to left, right? Up and down. So those again will be moving with probability 0.1 each. So this is how your transitions are designed based on the action you pick. And there is a notion of a reward you achieve. Okay, by the way, if let's say you are at one of the boundary cells, let's say here, and if I try to go to left, right, then there is no cell to the left, then essentially what's going to happen is that with probability 0.8, if the effect is to go to the left and there is no cell on the left, then I'll stay wherever I am. Okay. So for example, here, if I intend to go to left and that's the let's say with probability 0.8, I actually sort of end up going in my desired direction. So here essentially going in left corresponds to staying wherever I am. Okay. So for example, even here, if I intend to go to right and there is nothing to go to right to, then essentially in that case, I'll stay wherever I am. With probability 0.1 each, again, I might move in the orthogonal directions. So again, even in the orthogonal direction, if there is nothing you can reach up to, then you'll stay wherever you are. Okay. So for example, here, if I plan to take a move to the left, then with probability 0.8, I'll stay wherever I am. With probability 0.1, I might move up. With probability 0.1, I'm supposed to go down, but then again, in that case also, if the effect is to go down, then essentially I'll stay wherever I am. So here, for example, if I try to move to left, then with probability 0.9, I'll stay wherever I am because 0.8 corresponds to the moving left, and point 1 corresponds to moving down. In both cases, I'll stay wherever I am. So if I try to go to left from this particular start cell with probability 0.9, I'll stay wherever I am, and with probability 0.1, I'll go up. So essentially, this is just some sort of a nuance. But the idea which I wanted to give over here is that there is a notion of action, and based on those actions, you will make a transition to your state. So you'll transition in your state space. That's the main idea. Okay, and after this, essentially, uh, at each step, you are going to receive a reward. So there is a notion of a reward. So at each step, so you obtain a reward. So this reward is +1 and -1 for the two terminal cells. By the way, if you reach one of these two terminal cells, then essentially you will stay wherever you are and the game ends here. And you achieve a reward of +1 and -1 on those two cells, respectively. And you receive a reward of -0.04 on every other cell. So essentially, this is to penalize you for taking too long to reach your goal state. So if you keep stuck in the game, then essentially you will keep receiving that -0.04. Okay. So if we don't keep this reward, then essentially you might end up just sticking around in the game and never completing it. So this reward is just there to ensure that as time passes by, you are supposed to try to reach to the goal state. If not, then you will keep receiving some negative reward. Okay. So essentially, the goal over here is to maximize the cumulative reward, which is obtained over a sequence of steps. Maximize cumulative reward. And it's also called payoff. So these are all alternate terms for the reward, cumulative reward as well, which is sum over t RT. So time step t, you receive your reward RT, and then you need to maximize the total sum of rewards. So essentially, many other games, for example, Mario or whatever games you might have played in your childhood, they can also be formalized in this particular setup. We are not going to, discuss this game in too much depth, this specific game. But the idea over here was to, just understand some basic concepts. And now we'll try to formalize these using the notion of Markov decision processes. So essentially, we now want to formalize these ideas. Markov decision processes. So a Markov decision process, or an MDP, consists of the following. So now we are going to introduce some jargon, but since you now have some idea of this particular grid world game, you will be able to relate to this. So there is a collection of states, state space, or a collection of states, which I'm going to denote by S. So for example, in the grid world, the 11 cells which you have access to, those form your state space. Then there is an action space, or a set of actions. Right? So for example, the 4 possible actions we have at every cell, those form our action space in the grid world game. And then there is a reward function. So a reward function is a function from the states to reals. So I can denoted by R as a function of S, where S is a state. Sometimes reward functions can also be a function of both states and actions to reals. So you can denote it by RSA. Right? So these rewards can be positive or negative, as we have seen in the grid world example. And then there is a notion of a transition distribution, which is that if you are in a particular state, let's say S, and you take a particular action, what is the distribution over the next state which you might achieve? Right? So this is known as the transition distribution. And finally, you have a term which is called as discount factor, and I'll indicate with the Greek letter gamma. So this discount factor indicates, how much is the sort of weightage of a particular reward in future. So I'll actually come to this in some time. So basically, we'll visit this in some time. Okay, so just hold on to it right now. Okay, so this we'll revisit. Okay. So others we can actually relate to the example of grid world. For example, transition function also we have seen that if you are in this particular state, you pick an action of up, down, left, or right. And essentially, you might get to one of the corresponding cells, and there is a distribution associated with the next state given the current state and the action you pick. Uh, okay, so basically, so right now what we discussed was that our goal was to maximize the cumulative sum of rewards, right? So, okay, so now let's try to understand what this discount factor is. So naively, we might want to maximize, sum over T RT, or the total sum of rewards which we achieve, total cumulative sum of these rewards. But there can be some issues associated with it. So first is that, this particular sum can go off to infinity if you keep on collecting the rewards during the game. And actually, there is a notion of a finite horizon versus infinite horizon Markov decision processes. We are not going to discuss those in too much detail, but essentially, in some cases, you might want the game to end in a finite number of steps, which is called as finite horizon MDP. And in some cases, you may not want that. You might want to allow the game to continue till infinity. So typically, we deal with the infinite horizon MDPs because here, essentially, as we'll see, the analysis is essentially more simpler for infinite horizon, and that's what typically all textbooks and papers deal with. But in any case, for infinite horizon, your total mm, cumulative sum of rewards actually may go off to infinity, right? And that is something you may not want to have. So essentially, what you do is that you introduce something called as a discount factor. Okay. So instead of maximizing this, what we do is that we end up maximizing sum over T RT gamma to the power T, where gamma is some value which is less than. So you can check that, if all your rewards are upper bounded by some R max, right, then essentially this sum is going to be less than R max over 1 minus gamma, where R max is max over all as mod of Rs. Okay, so basically this is the maximum absolute value of the reward, then essentially this geometric sum, right? So this will be upper bounded by R max over 1 minus gamma. Okay. So there is another reason to introduce Rmax. One was this more of a mathematical reason, which was that you would want this sum to be bounded. The other reason, right? So one reason was that it gives an upper bound on the sum. So basically, this is the reason why we are trying to introduce the discount factor. The second reason, which is more from the economics perspective, is that a reward, like let's say if you get a dollar today versus a dollar tomorrow, you'll prefer a dollar today, right? Because tomorrow the value would have decreased. So essentially, so in economic terms, so it discounts for inflation. So more specifically, if the interest rate is R, for example, then the price is okay, the actual value of a dollar, or let's say a value of a 100 rupee note, that will go down with a factor of 1 over 1 plus R. So essentially, gamma, you can consider it like 1 over 1 plus R. So this R is not reward, this R is interest rate. Okay. So essentially, this you can interpret this in economic terms as well. And now, when you are trying to maximize RT gamma to the party, think of it this way that, okay, you receive a reward today, which is R naught, you receive a reward tomorrow, which is R1, but then you'll discount it in today's time by, factor of 1 over 1 plus R. Similarly, a reward 2 days later, worth today, it will be 1 over 1 plus R squared, so on. Okay. So overall, this is what we are trying, this is what our goal is. And essentially, now you can think of a sort of an agent or a player who is playing the game, and then an environment, right? So an agent, right? So given a state, an agent is supposed to respond with an action A, and based on this action and the current state S, the environment is supposed to go off to the next state S prime. Okay, and there is a specific distribution associated with it, which is the transition distribution. And the agent is also supposed to give a reward based on the new state S prime. So essentially, the environment, sorry. So essentially, you have two parties, agent and environment. Agent is the player. The player receives a particular state, okay, and then picks an action. Let's say you are a player of the particular grid world game. Based on the current state, you need to choose the next action. Based on the action you have chosen, the environment will lead you to the next state with a transition distribution. The environment will also give you a reward. So there is an interplay of this agent and environment which is constantly going on. And essentially, the agent has can maintain its own function of choosing the next action based on the current state. So that is called as a policy function. This policy function is a mapping from the set of states to the set of actions. So essentially, given the current state, the agent is supposed to pick the next action, and that is how the policy function is designed. This policy function can also be probabilistic. So it can also be a distribution of the next action to pick based on the current state. So there are two ways to interpret it. If it is deterministic, you can consider it as a function. If it is probabilistic, you can consider it as a conditional distribution. Right. So here you can call the policy to be either a deterministic policy, or it can be a stochastic policy. So it can be shown that if you want to maximize your expected payoff, then it is sufficient to choose deterministic policies. However, in some cases, like for example, for policy gradients, it might be useful to actually consider a probabilistic policy as well. Okay. And just to sort of conclude, so what the way the game starts is that you start with some particular start state or initial state, say S naught, and based on the start state, okay, based on the current state, you get a reward R naught, and the agent then picks an action A naught. Based on this A naught, the environment will move it to the next state S1, which is whose distribution is governed by P of S1 given A naught and S naught. And the environment will also give a reward R of S naught. Based on that, the agent will again pick an action A1 and so on. So the actions of the agent are governed by the policy function pi of S naught, or it can be, coming from a distribution of pi of A naught given S. So it can be deterministic or stochastic. So this entire sequence of states, rewards, actions, and so on, this is called as a trajectory. And one can think of, as the policy of which a particular agent will pick will be something to maximize the expectation over pi and p of s1 given a and s sum over t rt gamma to the power t. So conditioned on s naught equals to s. So essentially, this expectation is essentially over the choices of the agent as well as the choices of the environment. Typically, we assume that okay, the environment is always stochastic, but the agent can environment is generally stochastic, and there are deterministic environments as well. For example, for the game of chess, it is completely deterministic. The agent itself can be stochastic or deterministic, although in most circumstances deterministic agents do suffice. But then for modeling and learning these agents, it may make practical sense to have a probabilistic agent as well. That's it for today for this particular lecture. We'll continue in the next lecture, and we'll define something called as the value function, and then we'll see how to optimize that. Okay. For Markov decision processes. So thanks a lot. Hope you enjoyed the lecture. Do like and subscribe the video. Do like the video and subscribe to the channel and share it with your friends, batchmates, or colleagues. Okay, thanks a lot. Bye.